Hi, Professor Lee here. In this lecture, we're going to look at linked lists. This is chapter 16 of the textbook. We're not going to introduce everything that's in the chapter, but this will cover most of it. And we're going to look at how we might implement a linked list ourselves. And we're going to look at it in details, many of those functions, how we're going to operate on linked lists. So first of all, we have gone through an overview of various different data structures in our last lecture. And data, as we know, can be organized in a variety of different ways. You may use dynamic sets. Linked list is one of the dynamic sets. And then we may use trees and graphs. Now, of course, the simplest data structure would be an array. So if we're going to organize data sequentially, it's also called a sequential list. Now, there's a problem with the fixed size of the array, right? Well, first of all, array size is fixed. And an array, it may not be sorted. So when it's not sorted, searching for an item, it can be slow. If it's sorted, then the insertion and deletion can be slow. And that also requires, because once you insert an element, and then you need to move the rest of the element, or deletion likewise, so that it's contiguous elements sequentially. So that requires data movement. Now, linked list is, as we mentioned, a dynamic set. It's a collection of nodes or items or elements. There are many different names. It's the same thing. Now, each of the node, now using the terminology in this textbook, a node contains data. This is just a data we'll carry around, which I call the satellite data. And then you may have a link. This is talking about singly linked list. You may have a single link that points to the next node. If you have a doubly linked list, you're gonna have two links. One goes to the next, one goes to the previous one. So this structure of a linked list, just visually, may look like this in memory. You have a header pointer that points to the head of the list, the very first element or node. And then each of the nodes point to the next node. And the very last one has a no pointer because there's no more node. This just points to no. Now, the node, obviously you can use different ways to make up the node, the data structure for that node itself. It can be declared as a class or a structure. As I mentioned earlier, these two data types can be, they're almost equivalent, except some minor differences in default visibility of these members. If you declare a struct and the default members are public by default, if you declare a class, they're private by default, but you can always use different modifier, so you can make them either public or private. So there's not really a practical, not too much of a difference anymore. So here, let's say we assume we're going to use a structure as the textbook indicated. It works. but it doesn't really offer you much of the encapsulation. This may be fine in this case. So you're gonna have some information that you carry around. In some cases, this piece of information perhaps is the key of the element. But for the purpose of this example, let's not worry about that right now. So we have, a field, a member that's, just an integer. That's basically the useful information we're carrying around. Thinking of an integer array, this is the data we're carrying around. Then you have a link. So, so here we have an example again, and at the top of each node, you see an address, and it just, assuming hypothetically, this first node is at a memory location 2000, and the last one is a memory location 3600. Now every pointer, the value of the pointer is memory location, the address of this node. So in this case, the first one is 2000, which points to the next one, 2800. And if you use this expression, head, arrow, link, arrow, info, that means you're accessing the link field of this node, which actually points to this node, and then you're accessing the info field of this node, which is 92. And if we copy the value of head into a new pointer, so we declare a new pointer current, we may use this new pointer to traverse the list. So here's some properties. If the current, if you start with the head, it's the same value as the head pointer. And then you may access the info field, 17. Then if you access the link, which is 2800, that points to the second node. But the value of that pointer is 2800. And then you may access the info of that node, which is 92. Now, if we move this current pointer forward as we traverse from node 1 to node 2, then you basically, update the current pointer to point to this new node, which is from the previous current, which pointed to the first node, and then access the link field of that node, and then on the second node. So once we have here, so the value of a current pointer is 2800, and info 92, and the link is 1500. Link arrow info. That means what? Looking at this node now, the next one. So the value of that is 63. So what we just looked at is actually, using a pointer to traverse the list from one node to the next. And as we discussed earlier, the basic operations you may want to, search for item in the list. You may be inserting one or deleting one. And traversal basically means just to give a pointer to, if you have a pointer that points to the first node, it starts from the first node. And then it's basically just going through all the nodes of the list. So it's very simple to traverse a linked list. For a singly linked list, you can only traverse forward. So first we'll start with the head. And then we're going to loop through. And each time we're going to process the, we're going to maybe retrieve the current node and do something with it. And then we get the next node by accessing is link. And so by doing this for while loop, we'll go through all the nodes in the list. Now, the stopping condition is basically the very last one. Remember, the link field of very last node is no pointer. So if you have encountered that, then that stops. So as far as when we process the current node and do something with it, and let's say, well, I just want to output the info into console, and that's what it is. Of course, in real life examples, you're going to do much more meaningful things. Then now let's look at item insertion and deletion. Now recall we have a node type as a structure. Very simple. And let's say we're gonna declare a bunch of pointers. Well, we got the head. We got a P and a Q and new node. Let's see what they are. Now, to insert a new node, let's say the new node is gonna have info 50. And we want to insert this after P in the list. So suppose P is right here, pointing to the node with the info 65. And how do we insert a new node right after this current node pointed to by P? So first of all, let's construct a new node. So we'll make a new node, and the value of the info is 50. And what would be the link? The link of the new node, if we're going to insert this right after P, that means the new node should point to that node that's right next of a P. So imagine we have a node here that needs to point to this 34. So that's why we assign P's link to new node's link. And so now we have the new node that points to 34 now. Now we just need to have the current node pointed to by P pointing to this new node. So this new node is inserted that way. So that basically we're going to assign the new node as P's link. Well, we can look at this table, just see the effect of each of that statement. You construct a new node, and remember, this is just a visualization of what might be in the memory. And a new node pointer that points to a brand new object of node type. Then we assign 50 to info. Now we're going to update the link. We're going to assign the link of new node to point to the node with the info 34. And what's the address of this node? You can get that from P arrow link. Then the P arrow link now needs to point to this new node. So, it's assigned with this new node, which is a pointer. Then they point to the same object. So now you see this new list with the insertion of a new item. Let's look at the deletion. It's fairly similar. Now, suppose the P pointer points to 65, and we just want to delete the node that's next to it, which is 34. And to do that, if this is gone, that means P arrow link needs to point to the node after 34. So that's how it might look like this. Essentially, P arrow link is assigned with P arrow link. The P arrow link points to originally 34, and then that node's link is what we want, because we're going to need to bypass this node that we're deleting. Now, what happens if we just did that, and then, you know, the list, essentially after this operation, the list is okay now. As far as the list goes, now you have a modified list with the original node 34 to be essentially out of the picture, well, although the object is still there. So basically it means that's not complete. The memory is still being allocated for that old node 34. So we need to deallocate the memory to avoid a memory leak. And to do that, you still need to have something to point to this node. Otherwise, we don't have a way to deallocate. So we may use a helper pointer. We'll have a new pointer Q. So we're going to remember that node that we're going to delete first. Okay, so then we're going to update P's link to the node that's after it. So basically that's going to be Q error link. And once that's modified, and the list is good now, but let's deallocate this object pointed to by Q, basically the original node 34. And this is what it might look like in summary. So we're going to have a new pointer Q that's pointed to that node we're going to delete, and then modify the structure of the list. Then we deallocate Q, so that 34 is gone. So we've seen how to perform some basic operations on linked list. How do we construct a linked list? Starting from the beginning. Now, there are obviously different variants of linked list, as we mentioned earlier. It could be sorted or unsorted. Now let's assume it's unsorted. So if we're going to build a linked list, we can build it in two ways. We can build it in forward fashion or backward fashion. Building the forward meaning every time we need to insert a new node, we're going to put it in the very end of the list. And backward, that means we're going to insert in the beginning of the list. So let's look at it, building a linked list forward. So one way to do this is, let's have 3 pointers. One that points to the first node. And since we're building forward, this pointer is not going to change. And then we're going to have another one that's going to point to the very last node, so that we can insert a new node efficiently without traversing the holistic edge if we remember the last node. And then we'll have another pointer that's used to create a new node. So suppose we have the data elements 2, 15, 8, 24, 34. And then let's see if we can put them into a linked list. In the very beginning, first and last pointers pointing to null. There are no pointers. And then let's start with the first one. We're going to be able to, create a new node with the value 2. And so the first and last, this is basically right now a list of a 1 node. So the first and last are the same, they point to the same node. And then the next pointer, while the link of this node goes to null, there's no other elements right now. Now we encounter node 15. We're gonna create a new node. And then we're gonna just connect this to 2. in forward fashion, we just kind of insert this in the very end at the tail. So that means we're going to basically modify the, we're gonna first update the link to point to this new node, the link of node 2. And then the last pointer needs to point to that new node. That's now the new last node. So you repeat for every one of those values. Now you have a linked list. And the very end is just like this. The last pointer points to the very last node. Building this backward, again, is pretty similar. So you basically just initialize your first to-be node pointer, and then you're going to start with every node. You're going to create a new node, put the data in the new node, insert the new node before the first one. We have seen the insertion before. Then we'll update the value of the pointer first to point to that new node, which is the new first node. Now let's look at a linked list as ADT, abstract data type. So we're talking about ADT a lot because it is the public interface of some module, a piece of code, and that code may use data structure to implement that ADT. And the ADT offers, certain functionality that will be useful in certain situations. Now, if you have a linked list ADT, then you may have certain operations. You can initialize the list, decide if it's empty or not, print this out, find the length of it. You may destroy it, retrieve the information that's carried around, or search for an item. You can also insert, delete, or even copy the list. So these operations sort of define what you can do with a linked list, as from the outside. If you have another object that want to interact with a list, and that's what it can do with a linked list. So one way to classify linked list, of course, just one of the attributes, it would be sorted or unsorted. And so the algorithm to implement the operations, search, insert, and remove, they're going to be a little different if they are sorted versus unsorted. Now, let's say we're going to have a abstract class, linked list type, that will implement the basic linked list operations. And then a way to structure the relationship with sorted versus unsorted, you may have this as the parent class, and then you have these two classes that you inherit from that because it's mostly the same, but there's a minor differences in certain operations. So we can have a design of these different classes. So that one is unordered, another one is ordered, or sorted or unsorted is the same thing. So for an unordered list, when you insert a new item, at the beginning or at the end, if it's, and then you just basically insert the item at the end or the beginning. When you're building the list up. So building a list actually use two functions. You're going to insert first or insert last. So as we defined in the beginning, the structure of a node has two member variables. And over here, we are looking at a template structure. So previously we looked at just integers. Well, of course, you see the information we carry around doesn't have to be an integer. It can be anything. It's the satellite data. It can be another object. So the same operations we just explained can work on any type of an object. So that's why we can have a class variable type. And so this is going to work for any type of node. And then the linked list type, the actual linked list, it will have three member variables. Has a pointer that points to the first one, a pointer that points to the last one, and also we're going to remember the number of nodes in the list so that when we query how many nodes are there in the list, we don't have to traverse the list and count it. So it's going to be always up to date. We keep these variables protected so that the child classes, the subclasses of this, such as the ordered, unordered linked list, they can access these. Well, the processing of traversing the list, we can use an object for traversal. The object is typically called iterator. And the iterator is actually a design pattern. We have now introduced design patterns in object-oriented programming. There is a very good book on that. Iterator is one of the common design patterns. It's an object that produces each element of a container, one element at a time. There are two common operations you can do with the iterator to increment, basically to move on to the next node, and then also to retrieve the value pointed to by the iterator, the current, the current value that's dereferencing. So these two operators, if one of this to operate on this new object, they would have to be overloaded. So let's say the iterator class is called linked list iterator. And these iterators will operate on objects of a linked list type. This iterator will have a one member variable. Let's take a look at this class diagram in UML. So this iterator maintains a pointer of the current location in the list that it's traversing. And we have overloaded a couple of operators. The dereferencing operator to retrieve the current value of the node, which is type, the info field of the node. And then the increment operator that will return the next node, if there is one. If there's nothing, is no pointer. And then the equality comparison operator to compare if two iterators are the same or not equal. And the linked list type, as we discussed, some of those basic operations we can do with this as an ADT. Now remember, C++ classes are modeled based on the concept of ADT. So this class structure defines what this linked list type as an ADT. It has 3 protected fields, as we just explained, and a bunch of operations you can do with it. And there's a private function copy list that's used internally. So let's look at the default constructor. The default constructor of linked list type, again, this is a template function because everything about this ADT is templatized based on the class type, because the information you carry around can be any type. Initializing the 3 the 3 variables, first, last, and count. If we want to destroy it, now we need to deallocate all the nodes so that we're releasing all the memory. So basically we need a traversal. So let's have a temporary pointer, temp, and remember that while loop we saw before for traversal, just when we need to access the whole list. So here we're also using the first pointer. Every time as we deallocate the very first node, and then the first pointer moves on to the next node. So now we're going to delete the old first node. So once that is done, well, the last node is also going to be a no pointer. So now with this operation, the list becomes empty. How do we initialize a list? To initialize a list into empty state, we'll simply destroy the list if it has any nodes. Let's say we want to do something interesting with the list. Let's say we just want to print out all the info of each node. Again, is another traversal that we've seen this before. Just access every node's info sequentially, and then we're done. So we have this variable that actually remembers the size of the list. So this is a very straightforward. Somebody just return the value of that variable, count. That will give you the size or the length of the list. If you want to retrieve the data of the first or last node, again, straightforward. We simply just access the information pointed to by the first and last pointers. Begin. Now, begin and end, these are 2 operations that are using the iterator pattern. And here an example that I've shown is the end function. So basically when you begin, we just create a new iterator that's going to point to the very first node in the list. When you end it, you essentially just return a no pointer, because we're returning the node that's going to be passed in the last node, because at the time we end it, the iterator was pointing to the very last node. So at this time when we end it, it's actually just a no pointer. And by doing this, by the way, we're actually initializing the iterator with a no pointer. So the actual iterator is pointing to null now. To copy a list. So I'm not going to show code here. It's very straightforward. It's pretty much, you know, the steps just involved again is like this. It's very much like constructing a new list. So you create a node called a new node, and then you copy the info of the original node into the new node, and then you insert the new node at the beginning of the list. So you kind of building that list, you know, either forward or backward. And in this case, what is shown here is just saying, well, you can just build it forward. Either way, it works. So this is actually the code, what the code might look like. Pretty straightforward. Let's say you have a pointer that's going to point to the new node, and you have the current pointer that's used to traverse the list. And now if the list is not empty, we're going to make it empty. So basically, we're trying to copy a list that's provided as a parameter of the list into this current list object. So if the other list is also empty, then we're just returning an empty list like this. If it's not empty, first we're going to copy the first pointer so that you know, the current pointer points to the first one. We're also going to get the count. Then we'll create the first node. Essentially, trying to make a copy, and then we'll copy that very first node. And then the last pointer of this new list we're constructing is pointed to the very first node. So it's thinking of we're constructing a new list. Now we're going to move on to the next one by, you know, now we're going to update current pointer to the current's link. Now remember, current is pointing to the other list first node. So this is going to give us the next node. And so we're going to just do a loop here. This logic is very much like what you see before. So we're going to copy. There's a way to simplify this, by the way. This is just one way of doing it. You see some duplication of a code if you kind of observe that with the first node. And this obviously you can look at how to improve this as your own exercise if you want. And destructor. So this is the default destructor with the tilde of the class name. And then in that method, obviously, we already implemented destroy list. And so it simply just invokes that. And also, if we're going to assign the list to another one, we want to do a deep copy. And so essentially the assignment, if we override the assignment operator, you're assigning another list to a new list. Now here, first we're going to check, is that the same list? If it's the same list, don't do anything, just return the current list. If it's not the same list, we're going to simply just do a copy. So the assignment is a copy. That's pretty much it for this lecture. I've provided the code for linked lists and other variants in the goodie bag repo. So you're welcome to check that out. And if you have any questions, let me know. Bye-bye.